Hello everyone. Have you ever wondered why the nucleus of an atom seems a little lighter than the total weight of all its protons and neutrons put together? It's like when you try to carry a bag full of groceries but find it mysteriously lighter than expected, except here, physics has a very cool explanation. Before I spill the beans, here's a little joke. Why did the proton bring a suitcase to the nucleus party? Because it was carrying mass but didn't want to lose it. Okay, maybe not the best, but bear with me. Now, let's get into the concept of mass defect. When you add up the masses of all the protons and neutrons, also called nucleons, inside an atomic nucleus, the actual mass of the nucleus is less than this sum. This difference is called the mass defect, which we write as delta m equals z times m sub p plus open bracket a minus z close bracket times m sub n minus m. Here, z is the number of protons, m sub p is the mass of one proton, a is the total number of nucleons, m sub n is the mass of one neutron, and m is the actual mass of the nucleus. So, the mass defect delta m measures how much mass has disappeared compared to separate nucleons. But where did this mass go? This is where Einstein enters the scene with the famous mass-energy equivalence equation. The binding energy, E sub b, equals mass defect delta m multiplied by c squared, where c is the speed of light, 3 times 10 to the power of 8 meters per second. This tells us that the missing mass has been converted into energy, specifically, the energy that holds the nucleus together, called binding energy. Think of it like this: when nucleons bind tightly to form a nucleus, a chunk of mass turns into energy, which is released, almost like the warmth from a campfire representing that hidden energy. And to break a nucleus apart, you'd need to supply exactly this binding energy, kind of like paying an energy toll to tear apart old friends that are sticking together. This is why the nucleus feels lighter but stronger. One more interesting thing, binding energy per nucleon, that's the total binding energy divided by the total number of nucleons, tells us how stable a nucleus is. The higher this energy per nucleon, the more tightly the nucleus is bound and the more stable it becomes. Elements around iron have the highest binding energy per nucleon, making them the heavyweight champions of nuclear stability. So next time you hear mass defect, remember it's not lost, it's transformed into a powerful energy keeping the heart of the atom intact. Welcome back. Let's talk about a fascinating graph that nuclear physicists love, the binding energy curve, where we plot the binding energy per nucleon against the mass number A, which means the total number of nucleons. Imagine it as a roller coaster ride of nuclear stability. This curve shows us a clear trend. Medium-weight nuclei are the most stable passengers on this ride. If you look at light nuclei, those with mass numbers less than 20, their binding energy per nucleon is relatively low. Think of these nucleons as new friends at a party who aren't quite sure how to hold hands firmly yet. But when these light nuclei fuse to create a heavier nucleus, they release energy because the new nucleus has a higher binding energy per nucleon. So fusion is like friends joining hands tighter and throwing a joyous party that releases energy. On the other end, very heavy nuclei with mass numbers greater than 200 also have lower binding energy per nucleon. These heavy nuclei are a bit unstable at the party, holding on loosely. When such a heavy nucleus splits or fissions into smaller nuclei, the pieces have higher binding energy per nucleon. This splitting releases a burst of energy almost like fireworks at the party. At the peak of this curve sits iron with a mass number around 56. Iron's binding energy per nucleon is about 8.8 mega-electron volts, pronounced MeV, nuclear energy's own currency. This peak means iron nuclei are the most stable, like the perfect well-fixed handshake that everyone at the nuclear party dreams of. So, the binding energy curve is a nuclear map telling us which elements are the rock stars of stability and where energy can be gained by joining or breaking nuclei. Hello again. Now that we understand what binding energy means and how it varies, let's see how this knowledge powers nuclear reactions, both fission and fusion. In nuclear fission, a heavy nucleus splits into lighter nuclei. Picture a giant nucleus feeling crowded and deciding to break up into smaller family groups. These resulting fragments actually have higher binding energy per nucleon, which, as we learned, means they're more stable. This shift releases a tremendous amount of energy, which is why fission fuels nuclear power plants and atomic bombs. On the flip side, nuclear fusion is when two light nuclei merge to form a heavier nucleus. Imagine two shy dancers joining hands to form a stronger, more confident duo. Since the new nucleus has increased binding energy per nucleon, energy is also released here. This fusion process powers the sun and stars, lighting up life on Earth. The energy released in these reactions is calculated by the difference in total binding energies of the products and reactants. We write this as delta E equals the binding energy of the products minus the binding energy of the reactants. This difference tells us how much energy comes out or goes in. It's a bit like settling a bill after dinner. The energy balance must be clear. Importantly, nuclear reactions obey the conservation of mass energy. The lost mass delta M transforms into kinetic energy of particles and radiation energy. So mass isn't lost, it's converted, powering some of the most energetic processes in the universe. All in all, fission and fusion are nature's clever tricks of rearranging particles to release energy by improving nuclear stability. Let's roll up our sleeves and work through a real example to calculate binding energy. It's easier than baking a cake, I promise. Take the helium-4 nucleus, which has 2 protons and 2 neutrons. We are given the mass of a proton as 1.00728 atomic mass units, or U. The mass of a neutron is 1.00866 U, and the actual mass of the helium-4 nucleus is 4.00260 U. To find the mass defect delta M, we start by adding the masses of the individual nucleons, 2 times the proton mass plus 2 times the neutron mass, that's 2 times 1.00728 plus 2 times 1.00866. Calculating this sum gives us a number a little more than 4U. Now subtract the actual helium nucleus mass, 4.00260 U, from this sum. The result is the mass defect delta M equal to 0.03038 U. This tiny mass difference may seem insignificant, but it packs a punch. To find the binding energy, we convert this mass defect into energy using the factor that one atomic mass unit corresponds to 931.5 mega-electron volts. So, binding energy E sub B equals delta M multiplied by 931.5, which is 0.03038 times 931.5, giving us 28.30 mega-electron volts. That's a lot of energy stored in such a small nucleus. Finally, dividing this binding energy by the total number of nucleons, which is 4 for helium-4, gives us 7.08 MeV per nucleon. This high binding energy per nucleon tells us helium is super stable, making it a shining example of how mass defect translates directly into nuclear stability and energy. Pretty neat, right? Calculations like this are the backbone of nuclear physics. To wrap things up, let's quickly review the core ideas. Remember, the mass defect delta M is calculated by adding the total mass of protons, that is Z times M sub P, plus the total mass of neutrons, open bracket a minus Z close bracket times M sub N, and then subtracting the nuclear mass M. This difference is the mass missing, converted into binding energy E sub b by the equation E sub b equals delta m times c squared, where c is the speed of light. The binding energy per nucleon, E sub b divided by A, gives us a measure of nuclear stability, reaching a maximum near mass number A about 56, which is iron. Both nuclear fission and fusion release energy because the products have a higher total binding energy per nucleon than the reactants. Finally, when we say energy released in MeV, it's equal to the mass defect multiplied by 931.5. This neat relationship ties together mass, energy, and the forces that hold the nucleus together, unlocking the secrets of stars, power plants, and the fundamental building blocks of the universe. That's it for today's concept. Physics gets really fun when you can laugh and learn. See you next time.